Section 6.5, Sum and Difference Identities. So, I'm just going to give these to you without where they come from. And so if you want to see the derivation of these formulas, see me during office hours. We will go through them, but often enough this class doesn't have to see the derivation of this, and so we're going to skip it for now. Now, just to make sure you're okay with what we're reading, so for each one of these, notice that I have a plus and a minus. And so specifically, the idea is that if I have sine of alpha plus beta, that's going to be equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Similarly, if you were to change the sign, and instead of having plus here, and you had alpha minus beta, then that would just become minus. And so notice that when we're looking at the cosine formula, this is cosine of alpha plus or minus beta. And so if I had cosine of alpha plus beta, that's the same thing as cosine of alpha cosine of beta minus sine of alpha sine of beta. And then if I decided to swap the signs, just recognize that if I change the sign from plus to minus, then for cosine it becomes plus, okay? And so that's the way the formulas are read. Hopefully that clarifies that. Same thing down here with the tangent. Notice that if I'm using plus, then it's going to be a plus here and a minus here, whereas if I change that initial sign and it's minus, then this becomes minus and this becomes plus. And so I've just written this in such a way so that it's a single set of formulas for the doubles. But let's see this in practice. So the deal is that the sum and difference identities actually allow me to find the exact value of some of these functions when we plug in values that weren't on our unit circle. And so here, if I want to find the cosine of 15 degrees, essentially the idea is there a way that I could write 15 degrees as some alpha value plus some beta value, where alpha and beta are nice angles. And so specifically when I'm thinking about nice angles, realize that the list is short. They are reference angles of 30 degrees, 45 degrees, 60 degrees, 90 degrees, or any of the other quadrantial angles, or any of the other quadrants that have a reference angle of 30 degrees, 45 degrees, or 60 degrees. And so, again, instead of just saying 90, I could say quadrantial angles, and these are reference angles. At this point, the deal is like I say, we're trying to figure out, is there a way that I can write 15 degrees as some alpha plus beta, where alpha and beta are nice angles, 30 degrees, 45 degrees, 60 degrees, or iterations of those, or quadrantial angles. Well, honestly, I recognize that 30 and 45, that is 45 degrees minus 30 degrees, is going to equal 15 degrees. And so I believe that if we rewrite this as cosine of alpha being 45 degrees minus 30 degrees, then I can use the difference formula for cosine. So then refer to your handout where 45 degrees is alpha, 30 degrees is beta, and specifically we have subtraction. Then that means that we're going to have cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees times sine of 30 degrees. At this point, we can now actually find and evaluate each one of these exactly. So what's cosine of 45 degrees? That's going to be root 2 over 2. Cosine of 30 degrees is root 3 over 2. Sine of 45 degrees is again root 2 over 2. And sine of 30 degrees is going to be a half. Then fraction multiplication, root 2 times root 3 is square root of 6, divided by 2 times 2 is 4, plus root 2 times 1 is root 2 over 2 times 2 is 4. That's going to be root 6 plus root 2 divided by 4, and we're done. For cosine of 195 degrees, once again, we want to figure out we want to figure out, is there a way that we can write 195 degrees as some alpha plus beta or some alpha minus beta? And so since the last one we did subtraction, why don't we do addition here? I believe that 195 degrees could be rewritten as 150 degrees plus 45 degrees. And really I'm kind of using my unit circle to help me figure out what are good angles to use. 150 degrees is really a reference angle of 30 degrees in the second quadrant. 45 degrees is 45 degrees in the first quadrant, and so then this being cosine of 150 degrees plus 45 degrees, that's the same as using the difference, the sum identity. That's going to be cosine of 150 degrees times cosine of 45 degrees minus, remember that because it's plus now it's going to be minus sine of 150 degrees times sine of 45 degrees. Well then, cosine of 150 degrees, well that's going to be negative root 3 over 2, times cosine of 45 degrees, that's root 2 over 2, minus sine of 150 degrees, that's going to be positive a half, times sine of 45 degrees, that's going to be root 2 over 2. And we then get that this is negative root 3 times root 2, or negative root 6, divided by 4, minus 1 times root 2 is root 2, divided by 2 times 2 is 4. That's then equal to negative root 6 minus root 2, all divided by 4. And I don't see a way for this to simplify any further, and so we're done. Then if we have sine of 5 pi twelfths, recognize that 5 pi twelfths does not show up on my unit circle. So I'm trying to come up with a way to rewrite 5 pi twelfths as some alpha plus beta or some alpha minus beta. It doesn't matter which one, but we need to break it up into a sum or a difference of two nice angles. Well, in radians, our nice angles are going to be what? Well, of course, they're quadrantial angles, and pi sixths, pi fourths, and pi thirds. And iterations of pi sixths, pi fourths, and pi thirds. Really, I'm looking at my unit circle and the nice values that show up in radians. So now I'm thinking about 5 pi twelfths, and what in the world can I do? Well, if nothing else, maybe think about where you live with 5 pi twelfths. Well, 5 pi twelfths is less than pi halves, so it's going to be here somewhere. The only reason I want to know which quadrant I'm in is because it gives me the idea of where I should be looking on my unit circle to pick an alpha or a beta to start with. And so I think that my alpha and my beta are both going to come from quadrant 1, because if 5 pi twelfths is about there, I should be pretty close with stuff from quadrant 1. Now, if you don't see something to try, if you see a 12, well, you're probably going to want to use a third, or pi thirds, or pi sixths. So my thought is, why don't we say alpha is pi sixth? Let's try that. If alpha is pi sixth, then what's going to happen is then you get 5 pi twelfths is equal to pi sixth plus beta. Well, how about you subtract pi sixth? Subtract pi sixth, that gives me 5 pi twelfths minus pi sixth, which is really 2 pi twelfths, is equal to beta. But 5 minus 2 is going to be 3 pi twelfths. And 3 pi twelfths is really pi fourths. And so I recognize that if alpha is pi sixth, then beta is pi fourths. And so then I can rewrite sine of 5 pi twelfths as sine of pi sixth plus pi fourths, which then, using my sum identity for sine, that's going to be sine of pi sixth times cosine of pi fourths plus cosine of pi sixth times sine of pi fourths, and then sine of pi sixth, well, that's going to give me 1/2. Cosine of pi fourths is root 2 over 2 plus cosine of pi sixth, which is root 3 over 2. And then sine of pi fourths is root 2 over 2. And then this is going to give me root 2 over 4 plus root 6 over 4, which is then going to be root 2 plus root 6 over 4. I don't see this simplifying any further, and there we're done. Now I want to find the exact value of tangent of negative 15 degrees. Well, once again, I'm going to play that game of what quadrant I live in. Well, negative 15 degrees is here, just trying to keep myself on track. And since that's the case, I might want to use some combination of quadrant 1 and quadrant 2. And so we're really just trying to figure out, is there a way to write negative 15 degrees as some alpha plus beta, or some alpha minus beta? Once again, it doesn't matter which one. But part of me thinks maybe I want to do the subtraction. Because I see the negative 15, I'm thinking, what if I did 30 minus 45? So I think 30 degrees minus 45 degrees, there we are. 30 minus 45 gives me negative 15, and so then this is tangent of 30 degrees minus 45 degrees. Well then, using the tangent definition, that's going to be tangent of 30 degrees minus tangent of 45 degrees divided by 1 plus tangent of 30 degrees times tangent of 45 degrees. And so then, tangent of 30 degrees is root 3 over 2 minus tangent of 45 degrees, well that's root 2 over 2 divided by root 2 over 2, or 1, divided by 1 plus tangent of 30 degrees, that again is going to be root 3 over 2, times tangent of 45 degrees, which is again 1. And so here we get root 3 over 2 minus 1 divided by 1 plus root 3 over 2 times 1, which is just root 3 over 2. Now a couple things. If my labs will let you answer the question this way, go for it. There's nothing wrong with this answer. But if we need to clean it up, recognize that I can either combine like terms and do the bigger fraction division, which becomes fraction multiplication, or I could multiply by the least common denominator. There's a handful of things we can do. Let's multiply by the least common denominator on top and bottom. So I see that this complex fraction has all common denominators of 2. So I'm going to multiply by 1 in disguise. That's 2 over 2. That's then going to give me root 3 minus 2 divided by 2 plus root 3. Now, once again, there is nothing wrong with the solution. This is a good solution too. If my labs will take it, great. But if you need to get rid of the radical, remember that you can multiply by the conjugate of the denominator on top and bottom. That's going to be 2 minus root 3 divided by 2 minus root 3. And so then that would be 2 root 3 minus root 3 squared minus 4 plus 2 root 3 all divided by 2 minus 2 root 3 plus 2 root 3 minus root 3 squared. Then clean it up a little further. That's going to be 2 root 3 minus 3 minus 4 plus 2 root 3 all divided by 2 minus 3, which then will give me minus 3 minus 4 is negative 7. 2 root 3 plus 2 root 3 is plus 4 root 3, divided by 2 minus 3 is 1, made negative, and so then finally it cleans up to be, distribute the negative across the top, 7 minus 4 root 3. And so if they ask for a simplification, recognize that that will be what our simplification needs to be. But once again, there's nothing wrong with this solution or this solution in general unless they ask for a specific. Just like we can tear these things apart, we can put them back together. So notice that here I have cosine of 40 degrees times cosine of 80 degrees minus sine of 40 degrees sine of 80 degrees. And I'm thinking about what my formulas are. But since I have cosine, cosine, sine, sine, that's really going to be the cosine of alpha and beta, but because it's minus, that means that it's going to be plus. And so I recognize that alpha is 40 degrees, 80 is beta, and so at this point that's going to be really the same thing as cosine of alpha plus beta, which is 40 plus 80, which is the cosine of 120 degrees, and the cosine of 120 degrees is negative 1/2. And so that's the exact value of that statement. Let's do it again. Here I have sine of 62 degrees, cosine of 28 degrees, plus cosine of 62 degrees, sine of 28 degrees. Well, this is my alpha, beta, sine, cosine, cosine, sine. That's the sine sum, and sine matches, so that's going to be alpha plus beta. And so that's specifically going to be sine of 62 plus 28. These are both degrees. So then that's going to give me sine of 90 degrees, and sine of 90 degrees is, of course, 1. Here we have tangent of 13 degrees plus tangent of 91 degrees over 1 minus tangent of 13 degrees, tangent of 91 degrees. Well, I've got alpha, beta, and I recognize that this is really the same thing. I know that the numerator matches my tangent, and so this is going to be the tangent of alpha plus beta. And so that's going to be the tangent of 13 plus 91, which is the tangent of 104 degrees. Now, recognize that I've stated here no need to evaluate, because of course, if we're looking for exact values, this won't work. But this is an identity, and so there's a nicer way to write it, tangent of 104 degrees. Now let's find the exact value of this. What if I have cosine of pi halves minus theta? Well, what are we going to do with the theta? Well, we're just going to leave it as theta. There's nothing wrong with that. So let's actually see what we get. So using the difference identity for cosine, that's going to be cosine of pi halves times cosine of theta. For the cosine sum and difference, signs are swapped, so minus gives us plus sine of pi halves sine of theta. Alright, let's clean this up. What's cosine of pi halves? Cosine of pi halves is 0. But then 0 times cosine of theta, that's just going to be 0, but I'll write it for the moment. Then sine of pi halves, that's going to be 1. And then that's times sine of theta, which means that this is really sine of theta. And that's kind of interesting. But I want you to think about this for a moment. What if I just thought about the graph and the transformations of these things? Maybe it's useful to remember that if I rewrite this, I could rewrite this as cosine of negative theta plus pi halves. I can factor out the negative 1, and cosine is an even function, which means this is the same thing as cosine of theta minus pi halves. And my claim is that cosine of theta minus pi halves is the same thing as sine of theta. Well, in terms of the graph, what does this mean? This means that if you take the cosine function and you shift it to the right a distance of pi halves, you'll get the sine function. But we already knew this. Remember, we talked about sine and cosine being related by a phase shift. So specifically, this is going to come up again as an identity later for us, but this is one of what's going to be called the cofunction identities. Well, sine of pi halves plus theta, if you were to think about the graph, that's really asking the question, what if you took the sine function and you shifted it left pi halves? Well, what does that look like? But I claim we can figure that out using the sum and difference identities. So the sine is going to be sine of pi halves times cosine of theta plus cosine of pi halves times sine of theta. Well, what's sine of pi halves? Sine of pi halves is 1, and so this is 1 times cosine of theta plus cosine of pi halves is 0, and then 0 times sine of theta. That's going to give me just cosine of theta. And so once again, we get this other, what's going to be called later as a cofunction identity. Sine of theta plus pi halves is equal to cosine of theta. And if you think about this in terms of the picture and the phase shift of the graphs of the functions, it should make sense. Alright, tangent of 2 pi minus theta. Let's try this using the sum difference identity. So tangent of alpha minus beta, that's going to be tangent of 2 pi minus tangent of theta divided by 1 plus tangent of 2 pi times tangent of theta. Now what should we expect here? Remember that tangent has a period of pi, and so if we go 2 pi rotations, I'm hoping that I just get tangent of negative theta. That's what I should get. Or remember that tangent function is odd, and so it should give me negative tangent of theta. So one of those is what I expect to get, but let's finish our calculations. Well, what's tangent of 2 pi? Well, that's going to be 0 minus tangent of theta divided by 1 plus tangent of 2 pi is 0 times tangent of theta. Well, that's going to give me negative tangent of theta divided by 1, which is of course negative tangent of theta. That's exactly what I expected to happen, so we're good to go. So the first thing we should recognize with cosine of sine inverse of 2/3 plus tangent inverse of negative 3/4 is that really, remember that inverse trig functions are angles. And so this is the same thing as alpha plus some beta, where alpha and beta are angle measurements. Now we're going to have a little bit of work to do to find the exact value, but let's get started by just breaking this up using the cosine sum definition. And so this is the same thing as cosine of sine inverse of 2/3 times cosine of tangent inverse of negative 3/4 minus sine of sine inverse of 2/3 times sine of tangent inverse of negative 3/4. Now, a couple things to notice. First off, this one's really easy right here because sine of sine inverse of 2/3. Because 2/3 is in the domain of sine inverse, then we're perfectly fine, and we're going to get that that's just 2/3, so that'll be great. But that's the only one that I see that simplifies nicely. So then we actually have to recall how in the world did we actually find these things when we were dealing with cosine of sine inverse of something and I wanted to find the exact value. Well, I have to be worried about what happens on the unit circle. And so if I have cosine of some alpha, so if I call this alpha, where of course sine inverse of 2/3 is alpha, then sine of alpha being equal to 2/3 is my situation, but because it's really sine inverse of 2/3, we know where we have to live on the unit circle. It has to be between negative pi halves and pi halves, and so thinking about all students take classes, that means we have to be in the first quadrant. And so since I've got to be in the first quadrant, I know that I've got my alpha, where my alpha is specifically here. Then I know that given the information here, I know that 3 is my radius, and so 3 is my radius, and my y is 2. And then if I can find the x, then I'll know my answer. And so using Pythagorean theorem, x squared plus 2 squared is equal to 3 squared. That gives me x squared plus 4 is equal to 9, minus 4 minus 4. X squared is equal to 5. Take the square root of both sides. I now get that x is equal to root 5. And if x is equal to root 5, then I'll be able to find cosine of alpha. And then this was sine of alpha, so that'll take care of those. But just because I'm going to go ahead and have to do it anyway, let's go ahead and deal with this beta. And so for beta, recognize that beta is my tangent inverse of negative 3/4. And so if I have beta is equal to tan inverse of negative 3/4, let's think about that for a moment. Well, where does that live on the unit circle? Well, this is a little odd because remember that my range of inverse tangent is between negative pi halves and pi halves, which means that since this is negative, all students take classes, that means that this angle beta has to live down here in quadrant 4. I don't get a choice in the matter. Strictly because of the range restrictions of the inverse tangent function, that's where it lives. Now this is going to be real odd because if I'm on the right side of the y-axis, that means that my x value is positive and my y value is negative, so that actually fixes exactly what I need. So specifically, my radius is still going to be positive, but this is then going to be negative 3 and 4. Okay, so then what's my radius? Well, my radius, r squared, is then going to be equal to negative 3 quantity squared plus 4 quantity squared, but that's just going to be 9 plus 16, and 9 plus 16 is 25, and so r squared being equal to 25, take the square root of both sides, I get that r is equal to 5. So now I can actually answer all of my questions here, because cosine of alpha is going to be the x over the r, or that's going to be root 5 over 3. Then cosine of tangent inverse of negative 3/4, or cosine of beta, well, cosine of beta is going to be 4 over 5, so that's 4/5. Then minus sine of sine inverse of 2/3, that's the easy one, that's just 2/3. And then sine of tan inverse of negative 3/4, that's really sine of beta. Sine of beta is going to be negative 3/5. Then what do we get? I can clean this up a little bit. That's going to be 4 root 5 divided by 15 minus, well, that's really negative 3 times negative, or positive 6/15. And then if we want to clean it up even further and write it as a single term, that's going to be 4 root 5 plus 6 divided by 15. 4 and 6 have a greatest common factor of 2, but 2 won't simplify with 15, and so there's our solution, and I claim we're finished.